Okay, we started this yesterday, but we're just going to go back over it and create a whole lesson all in one shot. So we're looking at interference and diffraction, and a British scientist named Young is the person who first proposed this experiment, and he thought that if he shone a monochromic light, monochromic meaning one color, that when he shone it through a piece of paper that had two slits in it, that he would see two slits on the other side. What he actually saw was more than two slits and what we call today an interference pattern. The reason that we call these two lines, if you look here, slits here and not holes or gaps or breaks, is because they're actually really close together. They're basically the distance of a wavelength separation. And if you remember wavelengths, we measure them in nanometers, which is times 10 to the negative 9. So that's why they're called slits. He concluded that all light must have the ability to diffract and interfere. And so diffraction is the ability of the wave to spread out as it passes through an opening. Okay, and so here's the light beam, probably a laser coming in, and it's regular waves. In here is a slit, and this opening here is relatively the same size as the wavelength, and it creates this diffraction pattern that we see. Okay? And so what happens is when you have more than one slit, you have those rounded pattern here interfering with another pattern. When we have wavelengths that are in sync with each other or in phase with each other, we call that constructive interference. And when we have waves that are out of phase with each other or going in opposite directions, we see what we call destructive interference. Constructive interference is what gives us the bright light that we see, whereas destructive interference is what we see, or what we don't see actually, it's the dark band. So here's a wave that's in phase. So this is wave A and this is wave B. They're traveling towards each other. And what happens is when they meet up, the amplitude or the height increases. So this is wave A and B combined together, and then they just travel on their regular way. A was traveling in that direction, and B was traveling in that direction. And people might say, well, do they come in and do they hit and go apart? They actually, if we were to, I'll show you a video where they use a slinky, and they actually pass through each other. If we're looking at destructive interference, we have waves that are out of sync or out of phase. This is wave A traveling in this direction. This is wave B traveling in this direction. And what we see when they meet is that they cancel each other out. What it looks like is wave A and wave B. Okay? And then again they continue on their way. A traveling in this direction and B traveling in this direction. Okay? Then we went on to look at this page, and what this diagram does, there's a lot of information in this image. And here we have, again, our monochromatic light coming in, and it's hitting two slits. So this is all shaded in here. There's a barrier there. Here's a barrier, and this is the barrier here. So the laser light is hitting this. Again, this distance here is very small. It's, again, nanometers small. So here's when the light passes through here, we see these waves here. And you will only see these nice round curves if the slit distance is roughly equal to the wavelength. And then it's coming in here as well, and we see it do this pattern through this opening. Okay, where we see this cross line here, where we see this line here, here, and here's the X, and here's the X, we see constructive. Again, through here, through these X points here. So those are when the waves are meeting in perfect sync. And again through here. And again through here. So those are waves that what we call in phase. Where we see this area here, the waves are out of sync, they're out of phase, and so we have destructive. We have these dark bands. Again here, the waves aren't in sync. Whoops, my bad. There should be another line here, I missed this one. So then in this area, you can see the waves don't match up. In this area here, they don't match up. In this area here, they don't match up. And so wherever we have that, we have destructive. Oh, that one's done. Okay. Now, the constructive, you can see, is the bright area. And you can see here that the destructive is the dark area. Not only do we call them constructive and destructive waves, we also call them maxima and minima. So where we have bright light here, this part here, we call this maxima. Okay, where we have the dark area here, we call that minima. You can think of it as maximum amount of light or minimum amount of light. They also have pseudonyms. We call these antinodes, and we call these nodes. These two words, antinodes and nodes, are going to become really important as we get further into this unit. So now, of course, with everything that we can apply math to mathematically figure out all different parts of information. And so when we look here, we see that we have wavelength, lambda, is equal to dx over nl, or we also have lambda is equal to d sine theta over n. Well, where do we find these things? D, I'm going to clear this up. distance here between this opening and this opening. That's the distance between the slits. That we call D. Lambda, of course, is the wavelength that was given to us. X is the distance from the central bright band. So this is the central bright band here. Okay? To another bright band. So this distance here, from here to here, is X. Length is the distance from the barrier to the screen that's receiving the image. That's the length. And then the angle here that we see, there's one bright line. Here's the central line. We can see this as being theta. Okay? So theta is the angle from the center of the slits to a bright band. The other thing that we need to know is the order of the bands. So here, from here to here, from here to here, here to here, here to here, are bandwidths. Widths. Okay, those are bandwidths for antinodes. So we can call this is the central line. So this is where, and we call this distance from here to here, or not distance, but that band jump as N. So from the central line to the first line is N1. Here, again, this is the central line. This is the next bandwidth. This is N1. This is from the central line, and we're 2 bands away. N is going to be equal to 2. If we had more bands, if there was another band here, N would be equal to 3, and so on down the line. Just because we're going down from the central line doesn't mean we need to give it a negative number. N is just indicating the number of bandwidths away from the central line. So here we go. X is the wavelength of the light. D is the distance between the slits. X is the distance from the central bright band, so the main one, to another bright band. L is the distance from the slit in the screen to the screen. And theta is the angle from the center of the slits to a bright band. N is the order number of the bright band. The distance between the slits in the screen, which is indicated by D, can also be indicated by a diffraction grating. And a diffraction grating is the number of slits there are in a set distance. Okay, and you'll be looking through these today. So these ones here that I'm going to let you work with today, these are, says right here that there's 13,500 lines per inch. So that indicates to you just how close these lines are together. The thing that you need to know here is that any units can be used as long as they're the same. Okay? So remember here we're working typically this is nanometers. So just pay attention to your units. D is going to have a unit, L is going to have a unit, and X is going to have a unit. N is just an order, it won't have one. So the equation, this is really important to understand. The equation lambda equals d sine theta over n can be used for any diffraction calculation, but lambda equals xd over nl can only be used when theta is less than 10 degrees. And you can use simple geometry to figure out an angle through this here. So this here is your L. Okay, it's your distance between the slits in the screen. This distance here is your X, which is your distance is your distance between right bands. Now don't forget, it can go this way too, right? Don't get hung up that it can only go in that direction. So theta then is this angle here. Okay? So when we use trigonometry, this is what we find. The tan of theta is equal to opposite over adjacent, x over L. So really important to understand this part here. This here and this here, that we can find the theta, the angle here through that method. Okay? So light falls on a pair of slits, 1.28 meters, or 1.28 times 10 to the negative 5 meters apart. That's pretty darn close. The maxima are 1.15 times 10 to the negative 1 meter apart, and the screen is 0.550 meters from the slits. What is the wavelength of the light? What information do we have? We always start with the information that we have. So light falls on a pair of slits, 1.28 times 10 to the negative 5. So this here apart. Okay? The maxima. So this is the central bright line to the next bright line, or from one bright line to its next closest neighbor. And the screen is 0.550 meters away. So that's the length of the distance. And it's looking for lambda. Okay? So let's do an angle test. L is 0.550 and X is 1.15 times 10 to the negative 1 meter. And then we're going to figure out theta. We get 11.8098 degrees. So this tells us here that we cannot use that's lambda over NL, because this is greater than 10 degrees. So then that means that we're going to use lambda is equal to d sine theta over n. Okay, the other thing that we don't have here is the n. Right here, the maxima, whoops, are, my smartboard's off. The maxima are 1.15 times 10 to the negative 1. That means that from this line here, this bright line, to this bright line, this distance is 1.15. So n is equal to 1. They're only 1 apart from each other. You could also say, if you wanted, but you don't have to. Okay? Next example. Calculate the angle of diffraction of the second order maximum produced by directing monochromic light with a wavelength of 4.3 times 10 to the negative 7 meters through a diffraction grating with 2 times 10 to the 5 lines per meter. So it's asking us to find theta. Okay, it's giving us n equals 2. It says that it has a wavelength 4.3 times 10 to the negative 7 meters, and that the distance is equal to 1 over 2.00 times 10 to the 5, which means that d is equal to 5.0 times 10 to the negative 6 meters. This is lines per meter. So we're looking for this unit here. Okay? Formula here. Oops, this is sine theta. Sorry. So you're going to do the inverse sine and you get 9.90 degrees. Okay? Because we can always use this formula, we can only use the other formula if it's 10 degrees and lower. If the distance between the slits was increased in a diffraction experiment similar to Young's experiment, how would the angle of diffraction change? Well, let's look at the formula. Lambda is equal to d sine theta over n. So we're asking how would the angle change? Which means that sine theta is proportional to 1 over distance. So if we increase the distance, what happens to sine? In an inverse relationship, okay? So if we increase the distance between the slits and the screen, then, no, if we increase the distance between the slits in and of themselves, in the inverse relationship, sine theta would then decrease. And if sine theta is going to decrease, theta is also going to decrease. If a blue laser was initially used in Young's double slit experiment, how would the distance between the bright bands change if a red laser was used instead? So we're changing lasers. So that means that the wavelength is changing. So it says, if a blue laser was initially used in Young's double slit experiment, how would the distance between the bright bands change if a red laser was used instead? Well, we can look at this relationship here. And we're looking at the distance between the bands. So we're looking for x, which is why we're choosing this formula. X doesn't exist in this one. Lambda equals, or x equals lambda NL over D, which says that then lambda x has a proportional relationship to wavelength, because that's what we're looking at. Wavelength is changing. So as your wavelength increases, your distance between the bright bands changes. Okay, so that's how you look at the theory of these questions here. So now I want you to try these questions. Practice problem 1 for sure. Practice problems 2 to 6. You might have to work a little bit at it. Don't be afraid to use your textbook to help you out. And then I want you to come back and look at the next lesson. There's also videos up that you can look at to help you understand if you just need a pictorial. It doesn't go through the formula in and of itself. It just looks at interference and diffraction.